This is Math 139, Section 2.4, Part B. We're now going to look at finding rational zeros in a situation where our polynomial is not easily factorable. We just looked at finding zeros when we could factor, but what if we can't? Okay. We're going to use something called the rational zeros theorem, sometimes called the rational root theorem, and it looks like this. If we've got a polynomial function, notice it's written in decreasing order or descending order, all coefficients integers. If that has a rational zero, rational just meaning a fraction, then we can write it in the form P over Q, and P will be a factor of A0, which notice is the last or constant term. Q is a factor of AN, which notice is the leading coefficient. Now these are just candidates. These are the forms of any rational zeros. It doesn't guarantee that the numbers that we find this way will be true zeros, so we'll have to check that. So that's where our notes come in. There is no guarantee that any polynomial even has a rational zero. This theorem only helps where there is at least one. Secondly, the theorem identifies potential rational zeros, P over Q, but we have to test them. They're like candidates. We need to see which ones or one actually works. To do this, we'll just substitute our possibilities, or our candidates, into f of x, and if the value is truly a zero of the function, then the result should be 0. To make checking faster and easier, we'll typically use technology, Desmos, or a graphing calculator, and use the table feature to do that checking. So let's try a problem or two. In our first example, we'd like to find all possible rational zeros identified by that rational zeros theorem, and then test to see which ones really work. So, I'm going to say my rational zeros are of the form P over Q. P has to be a factor of the constant term. So, when I think about the possibilities for P, I'm thinking 1 and 2, also -1 and -2. Right? Those are all factors of 2. Q has to be a factor of the leading coefficient, which in this case is just 1. And so either +1 or -1, the only possibilities for Q this time. So let's list all possible values of the fraction. I could get 1 divided by 1, which is 1, or 1 divided by -1, which is -1. 2 divided by 1, which is 2, or 2 divided by -1, which is -2. These are just going to be repeats of the ones we already have, so I think I'm done. So I have 4 possible rational zeros. To test them, we'll just take each of those 4 x values and substitute them into the original function, f of x, and see which one or ones actually give us 0 for an outcome. I'm going to make that a little bit quicker by doing it on the calculator. In the y equals, I'm going to put in my original function. And then I'll go to my table. Again, our candidates are possible zeros, 1, -1, 2, and -2. And I'm going to put all of those in for x values. we can see right away only one of us actually gives us a 0 for the function value. Just put these down. So when we substituted our candidates into the function, only x equals 2 was actually a 0. Actually gave a 0 for an output. So x equals 2 is the only rational 0. Since this was a third-degree polynomial, we would have expected 3 solutions, or 3 zeros. So somehow there must be a way to find two more, and we'll be talking about that in just a few more minutes. Let's practice this rational zeros process one more time first, though. In the second example, we have a fourth-degree polynomial, and I, again, want to think of all possible rational zeros, p over q. P this time is going to be a factor of 8. So let's think about all the possible factors of 8. 1 and negative 1, 2 and negative 2, 4 and negative 4, 8 and negative 8. 1, 2, 4, and 8 are all factors of 8. Put in the plus and minus. In the denominator, q, factors of 3. So 1 and negative 1, 3 and negative 3. Typically, when I think through the values of the fraction, every fraction I get is going to be either a plus or a minus. And so just to make things a little bit quicker, I'll usually write down plus or minus in front of each one. So plus or minus 1 divided by 1 or negative 1. And plus or minus 1 divided by the 3's. Same with the 2's. 2 divided either by the positive or negative 1 would be plus or minus 2. And then 2 divided by one of the 3's would be plus or minus 2/3. Going over to 4. 4 divided by plus or minus 1, plus or minus 4. And 4 divided by plus or minus 3, plus or minus 4/3. Finally, the 8's is going to give me 8 over the 1's, plus or minus 8, and 8 over the 3's, plus or minus 8/3. So we actually have 16 possibilities here, 16 candidates for rational zeros. Let's see what happens when we plug them in. I'm actually not going to write them all out this time. I'm just going to use the calculator to facilitate. So let's go in and put in our new function. Oops. There we go. And again, I'm going to try a table of values. And let's just put in all of these numbers that we just identified as possible rational zeros. We have 1 and negative 1, 1/3, and negative 1/3, 4 and negative 4. Oops, I skipped some. Let me just do 2 and negative 2. I'm going to stay in order here. 2 and negative 2. Of all of those first few, negative 1 was the only one that gave me a y value of 0. Let's go back and see if any other ones do. Let's see, we're up to the 2/3. I'm going to go back up to the top here. 2/3 and negative 2/3. Looks like the 2/3 also worked. 4 and negative 4. Neither of those worked. 4/3 and negative 4/3. Neither of those worked. And coming back up, 8 and negative 8. No zeros there. 8/3 and negative 8/3. No zeros there. So, this is it. Excuse me, I'll sneeze. The only two of all of our possible candidates that actually gave us 0 as an output were x equals negative 1 and x equals 2/3. All right, so here again, we got 2 solutions. We really would have expected 4, since this was a 4th degree polynomial. And in the next section, we'll go about seeing how we'd find those others.